so this is the video in AP Calculus over derivatives of trig functions. We are going to begin by looking at our two most basic trig function graphs, f of x equals sine of x and g of x equals cosine of x, to see if we can determine anything about their particular derivatives. So we will start first with f of x equals sine of x. So you'll see here that we have the graph of f of x equals sine of x from negative 2 pi to positive 2 pi. And when we're sketching the derivative f prime, you want to remember those things we know about derivatives. When the original function is increasing, the derivative is positive. When the original function is decreasing, the derivative is negative. When the original function is at a maximum or a minimum, a peak or a valley, then our derivative either equals 0 or does not exist. All of those things are going to help us in graphing the derivative of sine of x. So the first thing I actually would look for is the fact that there are multiple peaks and valleys to y equals sine x. For example, we will just start over here in the positive x direction at pi over 2. Pi over 2 is a maximum. If you were to try to sketch a tangent line there, the tangent line would be horizontal like that. So it would have 0 slope, which means the derivative of sine of x at pi over 2 would have a y-coordinate of 0. The same thing would apply over at 3 pi over 2. And then in the negative direction, that would happen at negative pi over 2 and negative 3 pi over 2. Then in between those points, starting, for example, all the way over on the left-hand side from negative 2 pi to negative 3 pi over 2, notice that the sine graph is increasing. So that would tell me that the graph of the derivative would need to be positive. And then from negative 3 pi over 2 to negative pi over 2, the sine graph is decreasing, so my derivative would need to be negative. And then from negative pi over 2 to positive pi over 2, sine of x is increasing, so my derivative would be positive. From pi over 2 to 3 pi over 2, sine of x is decreasing, so the derivative would be negative. And then finally, from 3 pi over 2 to 2 pi, sine of x is increasing, so the derivative would be positive. So I should have a derivative graph here that is above the x-axis, then below the x-axis, then above it, then below it, then above it. So the domain that I have shown here on this particular graph. The question then becomes, how far above or below the x-axis is it? I'm going to look at the places where it looks like my slopes here on the sine of x graph would be the steepest. It looks to me it would be, for example, at x equals 0. That's the steepest slope I would draw in. To the right of there, your slopes would start to taper off until you get to that horizontal slope at pi over 2. So at x equals 0, if my slope would be 1 there for that little pink tangent line that I drew, that would mean that my derivative would have a y-coordinate of 1 at x equals 0. You could look at the same sort of thing at x equals pi. That would be a slope of negative 1. And the same thing at 2 pi. And then going backwards, we would have a slope of negative 1 at negative pi and positive 1 at negative 2 pi. Just those points alone, you should hopefully kind of be seeing the shape of what your derivative most likely looks like. Do you have any idea what that function is that we just drew? Think about the trig graph that starts up at 1, goes high, middle, low, middle, high. That would be cosine of x. So the derivative of sine of x is cosine of x. So now I want you to take a minute and do the exact same process with cosine of x. Go through and sketch, find where the derivative would be 0, where it would be positive, where it would be negative, what those positive and negative values would be, and see if you can sketch in the derivative of cosine of x. So pause the video and give it a try for yourself. Okay, have a similar wave to the cosine of x graph, but obviously it's not the exact same. Now let's see if we can try to figure out what that function is. You may have been noticing some things. For example, the fact that it goes through the point 0, 0. That should hopefully immediately make you think of the sine graph. However, with the sine graph goes middle, high, middle, low, middle. This one goes middle, low, middle, high, low, middle. That's the opposite of the sine graph. So this is actually the sine graph, but reflected over the x-axis. So the way that we reflect something over the x-axis is to make the function negative. So the derivative of cosine of x is negative sine of x. So looking at our 6 trig functions now, really, as long as you know the derivatives of sine and cosine, you could actually figure out the other 4 for yourself if you aren't able to memorize them. So we know that the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine x. Then let's think about the other 4. Well, secant is 1 over cosine. So, in fact, we could actually apply the quotient rule to 1 over cosine to figure out what the derivative of secant is. So the quotient rule is the bottom function times the derivative of the top, so that would be 0, minus the top function times the derivative of the bottom, so that would be negative sine x, all over the bottom squared. So that would be cosine squared x. So that gives us sine x over cosine squared, or we can think of it as cosine times cosine. If we think of it that way, we can actually kind of split this into 2 fractions. One would be sine over cosine, which hopefully you remember from pre-calculus is tangent x. And then 1 over cosine is secant x. So the derivative of secant is tangent x, secant x. Notice that both of these trig functions have x's in them. So it's not the tangent of the secant. It's tangent of x times secant of x. The other 3 could be found the same way by rewriting them. For example, you could rewrite tangent as sine over cosine, and then you could use quotient rule. But I'm not going to go through those for all of these. If you want, we can talk about them later on. But the derivative of tangent is secant squared x. The derivative of cosecant x is negative cotangent x times cosecant x. And then the derivative of cotangent x is negative cosecant squared x. These 6 derivatives are immensely important. You are going to see these for the rest of the year from here on out. You need to memorize them. Make yourself some note cards and start memorizing them today. So let's look at an example of where we can apply this. Here we've got a weight that's hanging from a spring, bobbing up and down like in your physics class. The position function for this weight is S equals 3 sine of t, where S is in meters and t is in seconds. What are the velocity and the acceleration at time t? So if you remember from what we've already discussed, or if you're in physics, which you've already learned in physics, is velocity is the derivative of position, and then acceleration is the derivative of velocity. So to find the velocity function, we would take the derivative of the position function. So the 3 will just come on down as the coefficient, and then we would worry about taking the derivative of sine of t. The derivative of sine of t would be cosine of t. And then the acceleration function is the derivative of velocity. So we would bring the 3 down again, and then the derivative of cosine is negative sine. So the acceleration function would be negative 3 sine of t. All right, so on the back of your notes, you have some practice problems now that would be wonderful if you could try before I see you in class tomorrow.